Hi guys, this is the solution video for part 1 of your test review. On these 5 problems that you'll see on part 1, remember that you will be able to use a basic calculator, so one of our red calculators for this part of the test. All right, so in our first problem, we have a quadratic, which is our parabolas, and we want to sketch the graph and find all the little pieces and parts. I'm going to start by rewriting my equation in standard form. Y equals negative 2x squared plus 12x minus 14. So that way I don't mix up any of my variables later on when I'm trying to do things. Now I noticed on the first quiz that we did, a lot of you, to find the vertex, used the completing the square method and tried to put the function in vertex form. That's probably the more difficult way to do this. So although that is an option, I'm going to use our quick little formula negative b over 2a to calculate the x-coordinate of my vertex. So the opposite of b is negative 12 in our problem. 2 times a, negative 2, which is negative 12 divided by negative 4, so that gives me a positive 3. Then to find the y-coordinate of the vertex, we're just going to plug 3 into our function. So negative 2 times 3 squared plus 12 times 3 minus 14. All right, so let's see, that gives me 9 times negative 2, that first term is going to be negative 18, plus 36, which will be a positive 18 when I add those together, minus 14 gives me 4. So my vertex, final answer for this first piece is the point 3, 4. I'm also going to jump down to the bottom here because I can answer this question from the original function. Which way does it open? Because my a value, the number in front of my x squared is negative, we can say that it opens down. And if you imagine a parabola opening down, you can also at that point say that you have a maximum value. All right, axis of symmetry. Remember, that's going to be that vertical line. You could even sketch it if you wanted to. That's going to cut right through my vertex. So don't forget x equals in front of it. That's an easy point to put that x equals there. And then it should always match the x coordinate of your vertex, which in this case is 3. The next thing that we're going to do is we're going to find the x-intercepts. Remember, an x-intercept is when y equals 0. So I'm going to set my function equal to 0. Oops. Negative 2x squared plus 12x minus 14. And then your options to solve this are either factoring, quadratic formula, or sometimes square roots. We can't use square roots here because I have an x squared and an x term. The first thing that I notice in this equation is everything is divisible by 2. Even better, if I divide everything by negative 2, I can get rid of that number in front of my x squared. So divide through negative 2, I'll end up with a negative 6x and a positive 7 at the end. Then we can see if it's factorable. Here we would be looking for two numbers that multiply to a positive 7 and add to a negative 6, which we don't have integers that do that. So my only option here is to use the quadratic formula. Make sure you know that for your test, because that's always going to be a backup if you get stuck factoring something or you just can't solve like this one. X equals opposite of b, positive 6, plus and minus square root. B squared is 36, minus 4 times a is 1, times c is 7, all over 2 times a, 2 times 1. So I'm going to have 6 plus and minus the square root. 36 minus 28 will give me 8, all over 2. I can break down that radical a little bit more. 8 is 4 and 2, so 2 square root 2 over 2. And then you can see all of my whole numbers there are divisible by 2. So 3 plus and minus 1 rad 2 all over 1. So those are going to be your exact x-intercepts. Now you can, for graphing purposes, approximate those. Square root 2 is about 1.4, so 3 plus 1.4 is going to give me about 4.4. 3 minus 1.4 is going to give me about 1.6. So I can graph those here and here. Y-intercepts a little bit easier. It's when my x is 0 And if you plug 0 in for x, that first term and the second term will cancel, and you're going to get, and we get y is -14, which is going to be way down here on our graph. But that should give us enough to connect these points and get a nice parabola. If you're not sure what it's supposed to look like, or you feel like there's a point that isn't quite fitting in with this parabola shape, remember guys, you can always make an XY table and just plot a bunch of points, and it can maybe help you check that your vertex is right, or that your X-intercepts make sense, or something like that. If it's opening the right way, that XY table is always an option. So you could always do what you can on it and then do the other problems, come back if you have extra time on the test, start just plotting some extra points, and use that as a way to check your answers. All right, let's go on to the next one. So next we have a polynomial function, and this first one is factored partially for us already. Hopefully you guys can look at this and see we've got that difference of squares right in the middle there, so we're going to factor that one a little bit further. That factors to x plus 2, x minus 2, and then don't forget x plus 5 squared, which you could always write x plus 5 twice there if you wanted to. And oh, there's also an x out front I almost forgot to write. Don't want to forget about that guy. Okay, so I'm going to do actually my zeros and their multiplicity first, since it's already factored for me. To find the zeros, you're just going to set each factor equal to 0. Don't forget about the 4x in the front. If I set 4x equal to 0, I'm going to get 0. If I set x plus 2 equal to 0, I get -2. If I set x minus 2 equal to 0, I'm going to get +2. And x plus 5 equal to 0, I'm going to get x equals -5. Then you want to name the multiplicity of each, which remember means how often that factor occurs. And every factor here occurs once, except x plus 5 occurs twice. We can see that from the power. So the first three all have a multiplicity of 1, because they occur one time. And the last one has a multiplicity of 2. All right, next we're going to name end behavior. To find the end behavior, you need two pieces of information. You need to know if your degree is even or odd. And usually we can look at a function if it's not factored and name the degree just by finding the highest power. But because this guy is factored already, you're going to have to count up your x's in your factors. So I have one x out front, an x and x plus 2, an x and x minus 2. So I've got 3 there, plus another 2 x's on my x plus 5 squared. So there's a total of 5 x's, 5 linear factors, which gives me a degree of 5. Also, your leading coefficient, you can see out front here, is -4. So the pieces of information I need to know is that my degree is odd and that my leading coefficient is negative, which remember there are 4 shapes of end behavior. Either both ends go up, both ends go down. It looks like a cubic going up, or in this case, it's going to look like a cubic function going down from left to right. Because it's odd, the end behaviors go in opposite directions, and because it's negative, it's going down. So now we want to list that formally. We're going to say x approaches -infinity and x approaches +infinity. And remember, that just means on the left and the right side of the graph what's happening. And from our little sketch, we can see on the left side it's going to go up. So that first y is +infinity. And on the right side, we can see in our picture that it's going to go down. So that second y is -infinity. My y-intercept, just like the last problem, is when my x is 0. So I'm going to go ahead and plug 0 in. 0 plus 2, 0 minus 2, 0 plus 5 squared. Well, I'm going to get a 0 out front times 2 times -2 times 5 squared is 25. And 0 times anything is just going to give me 0. Number of turning points, remember that is your degree minus 1, and we already did the work for the degree. So 5 minus 1 is 4. Sign analysis is an optional step. We'll come back to that in a minute. Let's go ahead and plot what we have. So on my x-axis, I have points at 0, -2, +2, and -5. I also know on the left, it's going to go up. On the right, it's going to go down. And I can now look at the multiplicities to see how to connect my dots. So remember, if you have an odd multiplicity like the first three, you're going to go through those x-intercepts. If you have an even multiplicity like -5, you're going to turn around or bounce off of that x-intercept. So as I connect things from left to right, the first thing I have to hit is -5, which has a multiplicity of 2, so I'm going to turn around. And remember, this is the part that's the sketch. There's going to be a little hill here. We don't know how high that is, but at some point we're going to turn around and get back to -2. Now, -2, 0, and +2 all have multiplicities of 1, so we're just going through. And then if you're doing it right, it should match up with that last end behavior, which says we're going to go down forever. Now, if you have trouble connecting the dots, option number 1 is make that XY table. Plot some points, plot the points until it makes sense. Option number 2 is you can do what we did kind of with our inequalities. Use some test points here. Separate your number line using all those zeros you found. And you can test each of these intervals just by plugging in numbers. And you can look at whether it is positive or negative. Now for this function, you're going to see plus, minus, which tells me before -5 and between -5 and -2, I'm above the x-axis. -2 to 0, I'm below the x-axis. 0 to 2, I'm above the x-axis, and below 2, or after 2, I'm below the x-axis. So that'll kind of tell you where the polynomial is located in with respect to the x-axis, if it's either above or below, and that again can help you kind of connect the dots and put these pieces of information together. Number 3 on your test, this will be the third and final graph. This is the rational functions that we just learned about. So remember, to start these problems out, you're going to factor the numerator and denominator completely. I'm going to start by factoring a 2 out of the numerator, which leaves me with x squared plus x minus 6. In the denominator, I'm just going to bring this down for now, x squared plus 3x minus 4. And then I think I can factor both of those quadratics. So bring my 2 down. My first numerator here, it's going to be what multiplies to -6 and adds to 1. That's +3 and -2. My denominator, we're looking for what multiplies to -4 and adds to 3. That's a +4 and a -1. And you can see that we've got no common factors there, nothing cancels, which means we do not have a hole in this graph. All right, starting with x-intercepts. Remember, a shortcut for the x-intercepts when you set y equal to 0 for these is you can just set your numerator equal to 0. As long as your numerator equals 0, you will evaluate to 0. Doesn't matter what you divide by. And it's already factored for us, which is nice. So you can just set those factors equal to 0. If I set 2 equal to 0, there's no x there, so that doesn't give me an answer. If I set x plus 3 equal to 0, I get an x-intercept at -3. And if I set x minus 2 equal to 0, I get an x-intercept of 2. And I'm going to go ahead and plot things as I go here. My x-axis, I have a point at -3 and +2. Y-intercepts are when x is 0. So I'm going to go ahead and plug that in. 2 times 0 plus 3, 0 minus 2. In my denominator, 0 plus 4, 0 minus 1. And on top I have 2 times 3 times -2 then. On the bottom I have 4 times -1. So let's see, that gives me a -12 over a -4, so a y-intercept of 3. Okay. Next up, vertical asymptotes. We're going to set our denominator equal to 0, which again, it's already factored, so that was worth the step in the beginning there. And if I set each of those factors equal to 0, I'm going to get x equals -4 and x equals 1. Don't forget the x equals on those because you're writing the equation of a line. So at -4, I have a vertical asymptote. And at +1, I have a vertical asymptote. There we go. Horizontal asymptotes and oblique. This is where we look at our n's and m's. So n, degree of my numerator, you can just look at the original problem for this, is a 2. M, degree of my denominator, also a 2. And they are equal. When they're equal, my horizontal asymptote begins with y equals. and then we divide the leading coefficient. Well, the leading coefficient on top is a 2, the leading coefficient on the bottom is a 1, so y equals 2 over 1, which simplifies to y equals 2. So y equals 2, we're going to make our horizontal asymptote, which means we do not have an oblique asymptote. Remember, it's either one or the other. Then it says find 3 additional points. Now, when we say additional points, we mean points that you don't have already. So you don't want to pick your X-intercepts or your Y-intercepts. We want extra stuff that's going to help us graph this. So I'm going to pick a point to the left of that first vertical asymptote, so maybe like -5. I'm going to pick a point in the middle here. I already have a point at -4 and 0, or at -3 and 0, so maybe I'll just pick -2. And then I already have a point at 2, so I'll pick something a little bit bigger than that, maybe a point at 3. And then you're going to plug these numbers into, you can use the original equation or you can use the equation on the bottom, and we want to evaluate them. I'm going to do the numerator and denominator separately, and then I'll reduce it if I need to. So if I plug -5 in the numerator, -5 squared, and of course you guys can use your calculator. -5 squared is 25 times 2 is 50. Then I'll have a -10, so that's a 40, minus another 12, that gives me 28 in the numerator. Denominator, -5 squared is 25. Then I'll have a -15, which is 10. -4 gives me 6. And that does reduce a little bit. 28 over 6, those are both divisible by 2, gives me 14 thirds. And 14 thirds is, let's see, 4 2/3. So it's going to be like up here somewhere. Okay, and that's enough to tell me that this branch, this kind of L-shaped branch we talked about, is going to be located in that upper quadrant there. It's going to be contained by those asymptotes we've already drawn. Let's plug in -2 in the numerator. -2 squared is 4 times 2 is 8. Then I'll have -4, so that'll take me back to 4. -12 gives me a -8 over. -2 in the denominator gives me 4. -6 -4, which gives me -6. -8 over -6 reduces to 4/3. Sorry, ignore the beep. 4/3 is 1 1/3. It's going to be right there. And remember, in the middle of these vertical asymptotes, you're looking for one of those end behavior shapes, and you guys can see this guy is increasing from left to right, so it's going to kind of look like a cubic function. It's going to start down here. We're not crossing those vertical asymptotes, and let's pretend that's a straight line. Looks something like that. Okay, and then let's plug in 3 to get something on the right side here. If I plug in 3, 3 squared is 9, times 2, that's 18, plus 6 will give me 24, minus 12, my numerator is 12. Plug 3 in the bottom, that's 9, plus another 9, that's 18, minus 4 is 14, and 12 over 14 reduces, those are both divisible by 2, to 6/7, so a little bit less than 1 at 3, right there. And you can see we've got a couple points down there, so that's enough to tell me that this kind of L-shaped branch is going to be located in that corner. Now again, last but not least, you want to check at the end, were there any holes? We didn't have any holes because we didn't have anything that reduced. If we did have a hole at a certain x value, we would just find that x value on the graph, erase the point that's located there, and put an open circle in its place. And this is another problem where, when in doubt, just start plotting a lot of points. If you're not sure what it's supposed to look like, let's get it like that, there we go. If you're not sure what it's supposed to look like, just plot points until you see the shape kind of come to life in front of you. And that's always something where, you know, on the test, if you're not sure about the graph is worth a couple points, but find all the other pieces and parts first, try to get all those little partial credit points, and then you can always come back at the end and connect those dots to get the rest of the graph when you've got time. All right, the fourth problem that you're going to see, this comes from section 3.5 if you're looking for extra practice problems. This is where we're finding all zeros, so we're looking for all solutions, given that we already have a 0. So the fact that we have a 0 means we do not need to use the P and Q method, although you could. P and Q method would be an option if you get stuck on this problem. Instead, when we have a 0, 3i in this case, that's our first answer, and because it's a degree 4, we know we're looking for 4 answers. 3i comes with a buddy. We called this the conjugate pairs theorem. Negative 3i, its conjugate, is also a 0. The next thing that we're going to do is write those zeros as factors. So this is where we put an x in front of it and change the sign. This works with radicals as well. And I also want to make a note. Let's say we had we did some like this. Maybe I had like 3 minus 4i. If you're writing that as a factor, remember to change both signs. So it'd be a minus 3 plus 4i when we put it into the factors. We get opposite values for everything. Once you do that, you can then take those factors and you can FOIL them together. Now here we just have 2 terms times 2 terms, so it's a quick little foiling. X times x, x squared. My outside terms are positive 3ix. My inside terms are negative 3ix, so those actually just cancel. And then your last terms, negative 3 and positive 3, negative 9i squared. You need to remember that I squared is equal to negative 1. So what we have here is a negative 9 times a negative 1, which is a positive 9. Remember, these problems could get a little bigger too. Like if you had that 3 plus 4i circumstance, you might have 3 terms in each of these factors. So your foiling would be a little bit larger. 3 terms times 3 terms, which would give you 9 terms. And I think there are a couple practice problems like that that you guys can look at in the extra practice in Polaris if you want to try a few of those. We also did a few in class if you want to see something a little bigger than this one. All right, so once we have this factor, the fact that we know it's a factor means we can divide it out. And when we divide it out, we're going to get a remainder of 0, which is great. And the quotient, the other factor, is going to give us the rest of the solutions that we're looking for. The only bad part here is you're dividing in a quadratic, so you have to use long division. But again, you have kind of a check within the problem that you're doing it right. You know you should get a 0 remainder. All right, so I'm going to put all my terms under my division bar here. There we go. Okay, and let's look at first. We're trying to find x squared times what gives me x to the 4th. That would be x squared. Then we're going to multiply x squared times everything on the side. That's x to the 4th, 9x squared, and we subtract. First terms cancel. 2x to the 3rd, just bring it down, negative 2x to the 3rd. Now be careful here, negative 6 minus 9 is a negative 15x squared, and bring down your other terms. Now we're going to do it again. X squared times what is going to give me negative 2x to the 3rd. Well, that's negative 2x. Times everything on the side is negative 2x to the 3rd minus 18x. Subtract, and you can see that both of those terms are the same, so those both cancel, leaving me with negative 15x squared and negative 135. Again, x squared times what gives me negative 15x squared, and that is negative 15, times the numbers on the side gives me negative 15x squared, and you guessed it, negative 135. Subtract, and as expected, we get a remainder of 0. So x squared plus 9, remember we knew that, but this quotient that we're getting, that's what we're looking for. That's the other factor that has our hidden other solution. So we're going to take our quotient, we're going to set it equal to 0. And then you can either factor again, quadratic formula, square roots. Can't do square roots for sure here because I have an x squared and an x term. So we're just going to factor 2 numbers that multiply to negative 15 and add to negative 2 are negative 5 and positive 3. Set each of those equal to 0 and we're going to get our answers. So final answers are positive 5, negative 3, and then don't forget we also had 3i at the beginning and negative 3i, which makes up our 4 solutions. If you want to check 5 and negative 3, because they are zeros, you can plug them in the function and make sure you get out 0, or you could divide them out with synthetic division and look for a 0 remainder. So again, something that if you've got some extra time on your test on Friday, you can go back and check those answers and see if they work. But if you're getting a 0 remainder, your quotient is more than likely correct. It would be pretty interesting to get that 0 remainder and be wrong at that point. So that's a pretty good sign on this problem. All right, one more problem that you have on the day one part of the test, and this is probably the fastest one out of all of them. We are determining if x minus 2 is a 0 of the following polynomial. And there are two ways to do this problem. I'll show you both of them. The first way to do it is to take x minus 2, set it equal to 0, and solve for x. Now this was called the remainder theorem. Oh, sorry, ignore the dog. We plug 2 into the function. 2 times 2 cubed plus 3 times 2 squared minus 2 plus 1. So I'm going to get, let's see, 8 times 2, that first term is 16. 2 squared is 4 times 3 is 12. Minus 2 plus 1. So that's a 28. Minus 2 is 26 plus 1. I get a 27. So my remainder is 27. Another way to do this is you could do your synthetic division. Your coefficients are 2, 3, -1, and 1. And that 2 is what goes in the box there. We're going to bring down our first term, multiply 4, add 7, multiply 14, add 13, multiply 26, add 27. And no matter which way you do it, you can see you get the same remainder. So now to answer the question, make sure you answer the question, is it a 0? The answer is no. It is not a 0. And then your explanation, this is all the work to support your explanation. The remainder is not equal to 0 would be the explanation as to why it is not a factor or a 0. All right, and that is going to be what you're going to see on day one of the test. Also, there will be a bonus on day one of the test, so keep that in mind. You might have a little extra time for that as well, get a couple bonus points. And then day two of the test, I'll make another video for you guys, and we'll have another extra day in between to be able to prepare for that second part. All right, let me know if you have questions in class over any of this, and I will see you guys soon.